All right, how are you guys doing today? We're going to do 14.3, which is the apportionment method. And I've already ran this section through with the face-to-face class, and I determined that some of the methods, i.e. Jefferson and Webster, take a really long time to discuss. So we're just going to focus on Alexander Hamilton. All right, so did you ever wonder why there's only 2 congressmen per state, but the House of Representatives can have quite a few depending on the state's population? How did our nation's leaders decide how many representatives each state received? All these questions will be answered in this section. By the way, to answer how many representatives we have, it basically depends on your population. So, like I said, we're just going to look at Hamilton's method. This is not the method that they use to use apportionment. However, it's probably the easiest one to understand, so that's why we're going to look at it. All right. The cool thing about apportionment methods is they can produce different results, which definitely can have an effect of how things get represented and causes fights. If you've seen the hit musical Hamilton, you will notice that Jefferson and Hamilton are always at political odds with each other. I'm not surprised to see that Hamilton and Jefferson both had their own method, apportionment, in terms of, doing representation in the Congress. So, objective number 1 says understanding what is a standard divisor and a standard quota. Before we look at different apportionment methods, we need to look and understand these 2 terms and how to calculate them. To find the standard divisor, you're going to take the total population and you're going to divide that by the number of items to be allocated. For the standard quota, we're going to take the population of a particular group divided by the standard divisor. So let's see how this works. A healthcare provider operating 5 medical clinics. This organization recently hired 60 doctors. Since the 5 medical clinics do not serve the same number of patients, the organization decides to apportion the 60 doctors based on the number of patients who visit each clinic. Here are the results. In Clinic A, they had 246 patients. In Clinic B, they have 201 patients. In Clinic C, they have 196, Clinic D, 211, Clinic E, 226, which gives a total of 1,080 patients. Find the standard divisor and the standard quota. By the way, you have to find the standard divisor first before you can find the standard quota. So the total population is 1,080. The number of doctors to be allocated in this particular situation was 60. So to find the standard divisor, I take the population and I divide it by the number to be allocated. So 1,080 divided by 60 equals 18. And that is my standard divisor. Next, we will find the standard quota. To find the standard quota, you take the number of patients served in each clinic in this case, and you're going to divide it by the standard divisor, which is 18. So we have 246. I'm going to divide that by 18. So I'm going to go ahead and write that out. 246 divided by 18. And I get 13.67. And I'm just rounding to the hundredths place. 201 divided by the standard divisor, which is 18, gives me 11.17. 196 divided by 18 gives me 10.89. 211 divided by 18 gives me 11.72. And 226 divided by 18 gives me 12.56. Now, if I add these numbers up, I should get pretty darn close to 60. And when I add these up, it's a little bit over, but it's 60.01. Okay, So next objective, we're going to look at the upper quota and the lower quota because the upper quota or the lower quota is used in different apportionment methods. So this is the same problem. We have clinic A, B, C, D, and E, and we have the standard quota because we just found them. So I'm just going to write those in. So for clinic A, the standard quota was 13.67. For B, it was 11.17. For C, it was 10.89. For D, it's 11.72. For E, it was 12.56, giving me a grand total of 60.01. Now, we have to know what the lower quota is and the upper quota. So rounding rules do not apply. What you do to find the lower quota is you take the standard quota and you round down to the nearest whole number. To find the upper quota, which by the way we are not going to use with the Hamilton method, but what you're going to do is you're going to take the standard quota and you round up to the nearest whole number. So to find the lower quota, I take 13.67, I turn that into just 13. Like I said, standard rounding rules do not apply. 11.17, I round that down to 11. 10.89, I round that down to 10. 11.72, I round that down to 11. 12.56, I round that down to 12. And when I add those up, I'm going to see that I only have 57. So I'm actually 3 doctors short. The upper quota, you round up. So 13.67 rounds up to 14. 11.17 rounds up to 12. 10.89 rounds up to 11. 11.72 rounds up to 12. 12.56 rounds up to 13. And when we do this, we get 62, which is over the amount of doctors that we have. We only have 60. So the lower quota will give you an under estimate, and the upper quota is going to give you an over estimate. All right. So we just went through this first piece, and now I'm on this example right here. Standard quota, let's say the standard quota is 13.42. The lower quota would be 13. Upper quota would be 14. So how do we apportion the doctors and have a fair system of doing so? This is honestly the million-dollar question here because it's really hard to find a really, truly fair system. So now we're going to look at one system that, is fair to a point, but it's called the Hamilton's method. And it is named after Alexander Hamilton. He was the first Secretary of the United States Treasury, and that is why he is featured on the $10 bill. He's called the $10 father. The story of his life is very popular right now because it is the contents of the hit musical Hamilton, which if you haven't seen, you got to see it. It's really great. Make sure you listen to the soundtrack first because it is very witty and very, very fast. All right, so the procedure for using the Hamilton's method of apportionment, the first thing you're going to do is you're going to calculate the standard divisor for the set of data. So that's the same thing we just did in objective 1 and 2. We're going to calculate each group's standard quota. We did that as well. And then we're going to round down. So we're going to take that lower quota and use it. Then, this is what's different. You're going to distribute any leftover items to groups with the largest fractional parts until the items are equally distributed. So let's go ahead and look at this next one. Use Hamilton's method to distribute 60 doctors for the 5 clinics previously described. So remember this. The standard divisor was 18, and we got that by taking the total population divided by 60. And remember, the standard quota, just to remind you, was 13.67 for A, 11.17 for B, 10.89 for C, 11.72 for D, and 12.56, which gave us a total of 60.01. Then, for the Hamilton's method, we take the lower quota. So this goes down to 13, 11, 10, 11, 12. And if we add those up, we're going to find out that we have 57. So we are 3 short. So here's where Hamilton's method comes into play. We look at clinic A, B, C, D, and E at the standard quota and find the highest fractional portion. So that 0.89 is pretty high. The next one would be 0.72 and 0.67. So what we're going to do is we're going to give each one of those an extra doctor. So instead of 13, I'm going to give them 1, so there they have 14. Instead of 10 for clinic C, I'm going to give them 1 more, so they have 11. Instead of 11 for clinic D, I'm going to give them 1 more, so they have 12. The other 2, B and E, I'm going to leave alone. So when I do that by apportioning the last 3 doctors, now when I add these up, I should have a value of 60 doctors, and I do. So once again, the standard divisor was 18. How did I get that? 1,080 divided by the 60 doctors equals 18. Okay? All right, so now we're going to look at another example, and it's going to require us to do a little bit of work. By the way, if you don't have a calculator out, you need to have one out because it's good to practice this before the test and before you do homework. So the next example says the Republic of Geranium needs to apportion 250 seats in legislation. Suppose that the population of Geranium is 8,800,000 and that there are 5 states in Geranium, A, B, C, D, and E. The 250 seats are to be divided among the 5 states according to their respective populations given in Table 14.29. So for state A, the population is 1,003,200. In B, it's 1,228,600. In C, it's 4,990,700. In D, it's 813,000. In E, it's 764,500, which gives us a grand total of 8,800,000 people. So it goes on to say, use Hamilton's method to apportion the seats. So I made you a chart. The first thing we have to do is find the standard divisor. To find the standard divisor, remember you take the total population, which in this case is 8,800,000, and we divide that by 250 legislative seats. So when I do that, the standard divisor is 35,200. Now I'm going to take each state A, B, C, D, and E and divide the population by the standard divisor to get the standard quota. So 1,003,200 divided by 35,200 gives me 28.5. 1,228,600 divided by 35,200 gives me 34.90. 4,990,700 divided by the standard divisor, which is 35,200, will give me 141.78. 813,000 divided by 35,200 gives me 23.09. 764,500 divided by 35,200 gives me 21.72. Now what I'm going to do is find the lower quota. So remember, you just round down. So I get 28, 34, 141, 23, and 21. And if I add those up, because I need to, I see I have 247. I am 3 short. And by the way, using Hamilton's method doesn't necessarily mean you're going to be 3 short It just happened in these two problems that you were 3 seats short. So I have to get 250. To do that, I'm going to pick the fractional part that's the highest, so 0.90. And I'm choosing 3 because that's how many I'm short. Okay, so for state A, it's going to stay at 28. For state B, I'm giving them 1 extra, so I get 35. For state C, I'm giving them 1 extra, so I get 142. For state D, it stays at 23. For state E, it becomes 1 more, which is 22. And if I add those up, I get 250, and that's exactly what I want. So that's Hamilton's method of apportionment. And if you look at the lower quota, because we used that to find Hamilton's method, it's the closest thing to it. The only problem is when you use the lower quota, you're going to be short. So Hamilton's method makes up for those missing delegates in this case. And I just want to go over one more thing, the quota rule. An apportionment for every group under consideration should always be either the upper quota or the lower quota. We will not be doing the Jefferson's method of apportionment. We're going to stop here. But please, if you are, curious, I don't want to stop you from being curious. You can look in the book on page, let's see here, I'll just tell you really quick, 889 is the Jefferson method, so you can follow along in the book with the notes. But like I said, you're only going to be required to know the Hamilton's method for the test. Okay, so next thing you're going to watch next week is a video by Khan Academy on the Electoral College, because it explains how we vote in this country. All right, take it easy. Bye.